All right, welcome back. Part two of three substitution methods paired with three equations. Where we left off last time, we had discussed how to decide which method goes with which equation. And we had done, kind of the first part of implementing the Bernoulli substitution to equation B. Today, we'll finish up that implementation of solving equation B. Then we will apply homogeneous sub to equation A, and then also miscellaneous, or a little miscellaneous sub there for equation C. So sounds like a lot to do, a lot of work, but it's okay. We have help. So let's dive in on the Bernoulli substitution. Where we left off last time was we ended up right here. We had implemented the Bernoulli substitution, which is v equals y to the 1 minus n. N in this case was minus 1. Therefore, we had v equals y squared. We plugged that in, and we got to this equation, which we then wanted to solve for v by integrating, right? So this right here was where we left off last time. The right-hand side of this was an integration by parts case, right? 2x times e to the minus 2x. Here I wrote out the details of that integration by parts. I sort of pre-wrote it just to speed things up a little bit, since this is kind of a Calc 2 exercise, right? You choose u to be the polynomial, choose dv to be the exponential, and then do the uv minus integral v du. There it is, right? There's the result. So there's that right-hand side. Once you have that integral calculated, then you just divide both sides by e to the minus 2x. Because remember what's on the left-hand side here, it's e to the minus 2xv. See over here, right, is e to the minus 2xv. I'm trying to solve for v, so I divide both sides by e to the minus 2x. Well, when I do that, this is obviously what I'm dividing by. That's going to cancel, cancel, cancel. And then here I'm dividing this by e to the minus 2x. Well, you have a negative power in the denominator, so bump that up to the numerator. That becomes then c e to the positive 2x, right? V then is y squared. That was our substitution. And then take the square root of both sides. There's your result, right? Y of x equals plus or minus square root of negative x minus 1/2 plus c e to the 2x for c, some real number. This plus or minus maybe looks a little strange having it in your solution at first. It's not a big deal. If you had an initial condition, you would know which it is, the plus or minus, right? So, you would just say, depending on whether the y coordinate of the given initial condition was positive or negative, you would know whether that would be plus or minus. So that's our general solution to equation B for the Bernoulli. B is for Bernoulli on some days. So that's our Bernoulli sub solution. Equation A, what's the plan here? We just to write out equation A again, there it is, dy dx equals x squared plus xy plus y squared over xy. We want to do this using homogeneous substitution. That's v equals y over x, or y equals vx, however you want to say it. And our promise with homogeneous substitution is that this will produce a separable differential equation, just like Bernoulli sub was promised to produce a first order linear equation that we could solve with integrating factors. Right here, we're going to get one that we can do the separation of variables. So let's do this. Let's take the substitution y equals vx, and let's plug that in for all the y's. So I'm taking this expression vx, and I'm going to put it here, 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 and here, right? That's your first step. So the derivative of vx equals x squared plus x vx, right, plus vx squared over x vx. The right-hand side isn't too bad because it's just algebra to clean that up a little bit, right? Just combine those powers of x, distribute those exponents. On the left-hand side is a little bit trickier. We need the product rule, right? We're taking a derivative of v times x. So use the product rule. Derivative of the first times the second plus the first times the derivative of the second. All right, well, the derivative of the second there is just 1, right? ddx of x, the derivative with respect to x of x, that's just 1. So the left-hand side becomes actually reasonably clean. The right-hand side cleans up too. Factor x squared out of that numerator, and we get 1 plus v squared over v. There's our right-hand side cleaned up. Subtract v from both sides. Right. And you'll see that it cleans up even further, right? We subtracted v from both sides, but then get a common denominator, make this v squared over v. Well, that's great because now these terms cancel. Subtract the fractions, right? And the v squareds go away. And now it's pretty clear. You could see this is separable, right? We can divide the function of v off of both sides. We could divide the function of x off of both sides. And so we did it, right? We separated our variables. Right, so now we can integrate both sides with respect to x. So let's do that. Let's integrate both sides with respect to x here. So when we integrate the right-hand side, not much happens. It's just log plus c, right? On the left-hand side, there's a little more to think about there. On the left-hand side, we have a rational function, and you need to do something like polynomial long division, right, to get that in a better form. It's often, you can think of that as the first step of a partial fraction decomposition. Here, you don't need to factor the denominator. It's just a linear factor. But you can do a polynomial long division to get the degree of the numerator strictly smaller than the degree of the denominator. So our quotient is 1. Our remainder is -1, right? And there's our better form that we can integrate, right? Thanks to the polynomial long division. So I have v, and then I have minus natural log of 1 plus v, and that's log of x plus c. All right. Now I just plug back in to get in terms of y and x, because again, remember, v isn't really part of the original problem. It's just a variable we made up to substitute, right? So v equals y over x. There's our y over x in each of those locations. The next thing that I want to do is clean it up a little bit more with properties of logarithms. I can make this x plus y over x, getting it as a common denominator. And then I can split off a term here. Right, using the fact that log of a quotient is subtraction. So then we get a double negative from the minus sign out in front of the log. I like this because it cancels that log of x term on the other side. Those go away, right? This is about as nice of a form as we're going to get for our general solution. So this, right, this is our implicit solution, right? It is going to be y over x minus log x plus y equals c, right, for c being some real number, right? So this is our implicit solution here. Why am I calling it an implicit solution? Well, because it's not an explicit formula for y in terms of x. I did not have this written as y of x equals and then some expression of x on the other side. Y is tangled up in two places, right? It's in that fraction. It's also in that logarithm. And no kind of algebra that I do, taking e to both sides, whatever, nothing I do is going to get us down to just a single y. At least nothing I can think of. Maybe you might think of something that I haven't thought of, but I don't know of an easy way to get this into an explicit form. So but still, this is an an implicit solution. What's nice is we can still check an implicit solution via differentiation. It's just you need to check using implicit differentiation, right? I didn't show checking the solution this time around with our Bernoulli equation up here, right? You can, because it would just be an ordinary derivative, and we've already maybe done a few like that in previous, if you've watched previous videos. But we haven't done one yet where we checked the validity of an implicit solution using implicit differentiation, right? So that's what I want to demonstrate now. So here, if I do implicit differentiation, I'm going to start with the quotient rule on that y over x, right? So I do my denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared, right? Then I'm going to do the derivative of the logarithm, which is just 1 over the inside function. But I do need chain rule here, right? So it's going to be 1 plus dy dx when we differentiate that inner function. The right-hand side, the derivative is just 0. So then I can solve for dy dx, right? Now this equation is all tangled up. So let's solve for dy dx. First, I'm going to multiply. I want to clear some of these fractions, right? There's just way too many fractions. So let's multiply everything by x squared. Right, that's looking quite a bit better. Let's then also multiply everything by x plus y. There we go. So now we don't have any fractions. So now I can expand everything out and put all the dy dx terms on one side and all the non-dy dx terms on the other side, right? So over here, let's see what we have. We have x squared plus xy, right? This is the dy dx terms that we have out front. Then there's one more dy dx term, which is going to be this negative x squared dy dx, right? That's this term right here is a negative x squared dy dx. And those are all the dy dx terms. Then we have all our non-dy dx terms, which I want to toss over to the other side of the equation. So what do I have? I have an xy, I have a y squared, and I have an x squared, right? And they're all negative on the left-hand side. So when you put them on the right-hand side, they all become positive. Then these x squareds cancel, right? So then I have just xy times dy dx. Okay, divide both sides by xy, and we end up with xy plus y squared plus x squared over xy. Ah, fabulous. This is exactly the original equation, equation A, right? So we recovered equation A successfully by differentiating both sides, by doing implicit differentiation on our implicit solution. So you can still check your result even if it's not an explicit solution. So you just need implicit differentiation, just like the word sounds, right? All right, so that's equation A. So we're done with equation A and B, Bernoulli and homogeneous substitutions. Now I want to demonstrate equation C, which was in some sense the simplest looking equation, right? It appeared the cleanest, but it was actually, in another way, the weirdest, because it doesn't fit into any standard technique. It doesn't fit into, or at least the standard ones I have listed here, right? It's not separable. You can't do separation of variables. It's not Bernoulli because it's not function of x times the power of y plus function of x times the first power of y. Right? It's not homogeneous because if you replace x by tx and y by ty, the t's do not just all vanish, right? They stay there in the denominator. So here we had to just guess something else, right? Miscellaneous substitution. This is a, hey, I hope this works kind of thing, right? This is the approach here. So that's what we want to implement, is this substitution. Why would I guess this? Well, I'm thinking of a differential equation, kind of like an integral doing u sub, right? This is sort of like a u sub. And sometimes it helps if you do u equals the denominator, right? X plus y, it's kind of a simple expression. I can see that maybe cleaning up the d, right? So it's nothing more than just hunch, a gut feeling, Mr. Spock. So let's do that. Let's implement this guess. So I have y equals v minus x because v equals x plus y. And now I can plug that into the differential equation. So y is going to become v minus x, right? And then here I have 1 over v, right? So I'm taking this and plugging it in for that y. And then the same here, I'm saying this is x plus y. Well, x plus y just becomes v, right? So I'm using both forms of that substitution. Then I do the derivative. Right? So I'm taking the derivative with respect to x of v is just dv dx. I take the derivative with respect to x of negative x is 1. And then I say, oh, this is lucky, it became separable, right? So it wasn't separable before, but now it is, right? Just add 1 to both sides. And you see we can actually do separation of variables. Right, and you can even make that v over v, right, to combine like terms, right? And it ends up looking a whole lot like the previous example, right? We have v over 1 plus v dv dx. And then, but here we have just 1 on the right-hand side instead of, in the previous case, we had x, I think it was, on the right-hand side, right? So here we actually already did this integral. Or sorry, we had 1 over x in the previous case. So here, yeah, we already did this integral on the left-hand side. So when you integrate both sides, I'm going to come up here. I'm going to just copy this integral because it was exactly the same. This step right here, right? When we had the integral of v over 1 plus v, it worked out to v minus log of 1 plus v. So I'm going to copy that down here, right? V minus log of 1 plus v. Now the right-hand side is different, of course, right? But that left-hand side, right? Just to show again what I'm doing. Where am I getting this from? I'm getting this from the previous example because we were doing integral of v over 1 plus v. So I'm just jumping right to that step, right? Because it's the same. And that's what's kind of cool. It doesn't matter that v represents a different substitution. At this phase of abstraction, it's the same. So there is our left-hand side. Then we can plug back in. We've already integrated the equation, so now we can plug back in for v, right? So v is then x plus y minus 1 plus x plus y equals x plus c, right? And once again, this is a great one to just leave as an implicit solution, right? I wouldn't try to solve this for y. Right, you have that 1y outside the log and 1y inside the log, and our chances of resolving that, to just the equation that's y of x equals some explicit formula of x, our chances are not good, right? So this is our implicit solution. All right, so there we have 3 equations. They all look kind of similar. It's all dy dx equals some rational function of x's and y's. But the techniques can be very different, right? So this is, I think, what's sometimes tricky about differential equations is the kind of like integration in Calc 2, right? You change one little thing about the integral or one little thing about the differential equation, and the technique all of a sudden is goes from this way over here, right? Yeah, it's kind of very sensitive to those little details. So, all right, thanks. So there's our session on substitution methods.